Good afternoon. So let's continue from where we left off in last class. We are almost nearing the end of the first module of this particular course, where we will deal with space groups and then teach you how to interpret them and construct crystals through simple MATLAB programs. Okay. So we stopped with realizing these 230 various space groups depending upon the symmetry operators that are possible in 3D space, including the screw rotation and the glide reflections. And we highlighted what those space groups were in yesterday's class, right? We just went through quickly what were the space groups and what unit cell or crystal system can be used in order to construct them, right? So now we want to start constructing a couple of these crystals using a combination of what we already learned with regards to using the MATLAB program to construct some simple structures, and also using the web page in order to identify appropriate Wyckoff positions so that we know where these atoms are going to go. Depending upon the space group that we will be dealing with, there might be some additional modifications that we will have to do to the code. Okay, so let us first open up the script that I shared with you this morning, which is called as genlat class exercise, and there are several different modifications to the original code that you had, right? The original code that you had was only able to create some FCC crystal structure, and another problem with that code was that you would not able to view the atoms that are belonging to just one unit cell. Usually it is convenient to view just one unit cell to see if you got it right. So there are certain additional modifications that have been done to this code in order to make that possible. Okay. So I will show you these lines where these modifications have been made. So if you have seen this code a couple of times, you will realize that most of these lines remain almost the same. So beginning from line number 49 to 112, most of the stuff remains the same, especially until line number 57. Okay, in the previous codes, I think you stopped with line number 57 and ended all the 3 or 4 for loops and then simply printed out the atom numbers or the atom details, right? But now what we want to do is we want to be checking whether this particular atom that has just been generated is actually lying within the unit cell. Okay, so there are a couple of different lines that we have here. So this is just based on simple analytical geometry. I don't want to be talking about the details as to why this works, but all I want you to do is have lines 61 through 78 in your code. 70, okay, you can have it until 74, but after that you basically check. If you do till 74, you will be generating certain values, and then you have to make a check here in line number 75. This is the line which is basically checking whether the particular point that you just generated lies within the unit cell or not. Okay. Now in this line number 75, you see these ones here. I am highlighting these ones here. You can actually increase these numbers to increase the number of points that will be printed out. So if you just put 1, it will just put exactly those atoms that are going to lie inside the unit cell. If you put 1.1, for example, it might show you even those atoms which are belonging to the adjacent unit cell. So depending upon that number there, you can actually control, how you want to view the unit cell that you just generated. Okay. In addition to that, there are a couple of different lines here also, which I have commented here. Add as many statements as required depending upon the number of atom types that you have, so that you can color or mark them in different sizes and plot them nicely. So these are the various lines right here. Okay. Now, so there are some other modifications also which have been done to the basis array, which is returned by the get basis function. So remember, the get basis function, what does it do? It basically gives you the set of all the set of points that you wanted to print out, right, in fractional coordinates. So previously the basis array contained only 3 columns and as many rows as there were basis atoms. Is that right? Do you all remember that? It contained it contained x, fractional x coordinate, fractional y coordinates and fractional z coordinates, and as many rows as there were basis atoms present in that particular crystal. Right now what happens is that the basis atom contains one additional column, okay, which represents an integer 1, 2, 3, 4, so on and so forth, representing some information on the atom, so that you can decide how to color it. So for example, basis 4th column, if you look at the 83rd line, I say if floor basis b comma 4 is equal to 1. So if it is atom type 1, and this would have been named in the get basis function, okay, we would have named the bth basis 4th column as 1 for some atom, and if it is that atom, then I want to give some size to it, size to print out, so that I am able to control the size of the circle that gets printed out in my MATLAB script, and I'm going to just say type of the atom is 1, so on and so forth. Okay, you can keep playing with this, and this one is basically the color. 100 represents the RGB color for this particular atom, and you can again play with this. So if it is atom of type 2, then I can change the color, I can change the size. If it is atom of type 3, then I can have a different size, I can have a different color, and you can add as many if statements as required depending upon the number of atom types that you have, and color them and plot them and have a good and visually inspect the crystal that you just generated. So this is something that should work for any crystal system, as long as you know how to construct it and give the right basis for this and choose the right lattice vectors. So these are the various lattice vectors which I am going to talk about today. You don't need so many. As you can see, I have commented some, and I am going to uncomment one by one depending upon which crystal structure I am going to discuss. Is that okay? So the first thing that I want to discuss, so this is just a set of integers going from 0 to 2 or 0 to whatever, right? And if you want to use this code in order to generate a data file, for example for the LAMPS program, but in that case it will not contain only one unit cell, it might contain large number of unit cells. You might want to analyze 10 by 10 by 10 unit cells, then you might have to modify this number to 10, 10, 10, and then not have these statements, right? Not have these statements, because this one will only store the atoms which will lie within the unit cell, within one unit cell, right? Or you can just put 10 here, and then it will store all the atoms which is lying within 10 unit cells. So in this manner you can actually modify this program pretty quickly in order to get the right number of unit cells, control them and visualize them. So before doing anything more complicated, let us try to generate a simple structure, and during this process we will learn a few things about centered lattices as well, and how to generate the Wyckoff positions for them as well. Yes. Yeah, and the one which I uploaded, the selenium part is not there. I have later on added that to demonstrate construction of a crystal lattice with this space group P3_121. So it's alright if it's not there. I will teach you how to construct it. You can modify the code in order to do that. Okay, it is going to be quite simple. The first one that I want to generate is not this. I want to start with the diamond. Okay, so the diamond, so I just uncomment those lines, okay, and I change this to diamond because this is what I have shared with you. I haven't shared the get basis command for the other crystal structures as well. I think I have shared with you only get basis _ diamond. Is that right this morning? Yeah. So now if you make these small changes, basically uncomment the lattice constants for diamond, uncomment the lattice vectors for diamond, and then get basis for diamond and click run, you should generate a structure, and this is basically the diamond structure. Okay, and you can of course view this in different ways. Okay, and this is the diamond structure. How many of you are convinced that this looks like the diamond structure? If you have seen it before, you will know that this is the diamond structure, right? And I have colored these atoms slightly differently. So I have have two different types of atoms here. In a sense, they both are carbon, but I have just colored them intentionally differently to show you that they are of different types. So what did I do in order to get this? Okay. So this is all the changes now are going to be in the get basis diamond file. So we can open the get basis diamond file. Okay. So this is the get basis diamond function, and what do we need to give here? We need to give the basis, the various basis atoms. But the manner in which we have been doing this class, we first need to know the corresponding space group and the corresponding Wyckoff position to which the carbon atom is going to be located in the diamond structure. So that will be given to us. Like I told you, that is going to be given to us. For the diamond carbon, the carbon is present at position 8A and it has the space group FD3 bar M. Okay, so what does F mean? Face centered. D mean there is a diamond glide. Okay, so that's the reason why the D is used, because that sort of a glide is present in diamond structures. 3 bar is 3 bar. Okay, and M is mirror. The third slot, that is the second slot after the F, basically contains a 3 FD3 bar, which means that it is a what unit cell will you use? Cubic unit cell. Okay, so from that it should be clear what your lattice vectors are supposed to be. Supposed to be A equal to B equal to C equal to some particular number, and alpha equal to beta equal to gamma is equal to 90 degrees. So now let us go to our crystallographic website, okay, and look at our space group FD3 bar M, which is number 227. Okay, and in that I said that it is belonging to position 8A. So at 8A there is one atom at 1 by 8, 1 by 8, 1 by 8, another one at 7 by 8, 3 by 8 and 3 by 8. So what I do there is I go to my MATLAB program and I give one atom at 1 by 8, 1 by 8, 1 by 8 followed by a 1, telling that is of atom type 1. Okay, and then B is 7 by 8, 3 by 8, 3 by 8 and followed by a 2, indicating that is of atom type 2. Okay, now it is not enough that I just do this, because there are just two basis atoms, but you will know that diamond structure has more than that inside one particular unit cell. You have just given two atoms right here. So how do we generate the other atoms? Okay, and even in the crystallographic website, you don't have anything else given right here. You just have these two, right? But whenever you have the centered lattices, that means those lattices which begin with a F or a I, right, or a or a C, right, like what would occur in A and C would occur in orthorhombic, right? You would go to the top and you would see something like this: 0 0 0 plus 0 half half plus half 0 half plus half half 0. Okay, so if you took each of those points that were generated, that were given to you, to each of them you have to add these centering coordinates to each. So to 0 0 0, that is to 1 by 8 1 by 8 1 by 8, I would have to add this, so I would generate 4 additional points, and then to 7 by 8 3 by 8 and 3 by 8, I would have to add this, then I would generate 4 additional points. Consequently, I have 8 different points present within the unit cell, which is why I have a multiplicity of 8 right here. So now that is again done inside the get basis command. So I say that A is 1 by 8 1 by 8 1 by 8 1, B is 7 by 8 3 by 8 3 by 8 2. Okay, then I have a new function called as basis underscore sim 8A. Okay, and what happens in that function? The following. So this is that function, basis underscore sim 8A. It takes in the x, which is this entire thing, right? It is taken in the A array, so it is taken that in the x right here, and I say the x fractional coordinate is x of 1, y fractional coordinate is x of 2, and z fractional coordinate is x of 3, and I develop another array by adding the appropriate components 0 0 0, half 0 half, sorry 0 half half, half 0 half and half half 0, and generate for those 4 additional points for each of those things. So first I give it to A. First I say basis underscore sim 8A A. So this small a now will contain those 4 additional points, right? Again I do the same thing for the B, where B is 7 by 8, 3 by 8, 3 by 8, 2, and I get that in this array C. So this A will contain 4 rows, C will contain 4 rows. The column vector will have to be retained. So all these atoms belong to this A type, right? 1. So anything that goes into A, I will have to retain x of 4 in the 4th column. So basis A 1, 2, 3, 4. The 4th column will contain x of 4, and x of 4 is basically having 1. Okay. Similarly, if you do for the Bth atom, the x of 4 will now contain 2, right? Once I receive A and C, I am going to return a concatenated array of the basis atoms containing even the information as to what the atom type is to the main program. Is that right? Now, in addition to this, there's something else that's been done here. Sometimes what can happen is, so 1 by 8, so 1 by 8 plus half, what is it going to be? 1 by 8 plus half, 5 by 8, okay. Sometimes 7 by 8 plus half, 11 by 8 becomes greater than 1, correct? Becomes greater than 1, okay. So 7 by 8 plus half, somewhere you are going to do plus half, right? It becomes greater than 1. So you have to keep track of these fractional coordinates which are actually going outside the unit cell and pull them back inside the unit cell. So if it becomes greater than 1, you will have to subtract 1. And at other instances, you may have negative x, negative y being specified. So if it is having a negative value, you might have to add 1 to it to pull it back inside the unit cell. So after actually assigning all these rows for the basis A, we write a for loop which will basically see if it is less than 0, if the values of the kth column for all the 4 different atoms, this 4 depends on how many basis atoms are being generated for that particular position. If it is less than 0, I will have to do 1 minus that, and if it is greater than 1, I will have to do that minus 1 to pull it back inside the unit cell. Okay. So this is what is being done always. These things are pretty much boilerplate. You only have to change a few things here in order to generate your other crystals. So once you do this, you can go back and click run, and you would generate your unit cell, and the unit cell also is all the your unit cell vectors are also marked. In a sense, your unit cell is nicely marked here, right? And you can actually examine that and see if what you have generated is correct before you actually go ahead and generate the entire structure in order to perform some analysis using your molecular dynamic simulation software. So this is the construction for simple diamond structure. Okay. Now we can go ahead and do, so now let us proceed to generate something a little bit more involved. Okay. I'm going to try to do PDS. Okay, before that, let me show you something else with respect to diamond also. Okay. So diamond, sometimes when you see the Wyckoff positions for the diamond, they would just say that there is an atom at 0, 0, 0, and there is another one at quarter, 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 right? That is how the diamond structure looks. So does this change anything here? Or sorry, 0, 0, 0, it's still a diamond structure, right? This is still a diamond structure. All that the crystallographic web page showed us was the fractional coordinate with respect to some other origin. We can always shift the origin in order to get the appropriate lattice or the Wyckoff positions, the x, y, z fractional coordinate for a given Wyckoff position. The same website can also give us the new sets of Wyckoff position for a shifted coordinate. So for example, right now I clicked the standard or default setting. When I click the standard or default setting, I got one set of Wyckoff positions, or XYZ coordinates for different positions, right? I may be able to do it for some other arbitrary non-conventional origin by simply specifying a origin shift. So where I went there was, I went to non-conventional setting and I said I want to shift the origin to 1 by 8, 1 by 8, 1 by 8, and then say change the basis. If I did that, you see that now I will have one table on the left hand side showing the standard or default setting, okay, and one table on the right showing the corresponding XYZ coordinates with the shifted origin. And in this case, I will have an atom at 0, 0, 0 and another one at 3/4, 1/4 and 1/4, which is what people are generally used to whenever they are dealing with diamond. So in this manner, whenever you are constructing these crystal structures with the crystallographic website, you need to be aware as to where the origin has been placed. Okay, and you need to at least not get confused whether the structure you are generating and the structure that you think you should get, whether they are same or whether they are different, is something that you should keep checking. Okay. Is there any reason as to why they shift the origin? So for some cases the location of the origin is obvious. Okay. For others, what happens is there are two or more locations where the origin can be placed, and usually the origin is placed in some symmetry element. So if you to address that issue, I will have to go to this materials project web page, and if you go to this particular site where you have the various possible space groups for carbon based materials, you go to this FD3 bar M, click on that. It shows you the structure, crystal structure, and here you will have a question mark, right? You have a question mark right beside the Hermann-Morgen symbol on this web page. After I clicked the specific space group, that basically opens up a diagram indicating all possible symmetry elements for the diamond structure, which is quite complicated, which is not very easy to read. Okay, so how did I go there? So I went there like this. So the materials project page, then I have all the structures based on carbon here. So I know that FD3 bar M is what I want to view. So I clicked on that. Okay. And this opens up. And then I scroll down and I see the Hermann-Morgen symbol and the corresponding question mark right there. I click on that and it opens up this web page. So the origin here is somewhere here, and it is not necessarily placed on an atom always, because FD3 bar M is probably the space group for so many different crystals. It is not necessary that it is it is for only for carbon diamond. Okay, and you can have several different possibilities, several different atom types coming up. So the origin is generally placed at the location of some symmetry element. So so there are two different choices that are present here. One is at the location of 3 bar M, and one other location is at 3 bar, the origin for this. So one is called origin choice 1 and other one is called as origin choice 2. The origin choice 2, which is basically used in the international tables of crystallography. But we didn't have to know all these things to actually go ahead and construct it. But the origin is generally known. You can read the international tables of crystallography and they will tell you where the origins are for specific space groups. Okay. So other things The reason why I wanted to highlight this diamond structure is that sometimes you will find only two lattice vector or two basis points, but to each of them you will have to add those centering operators in order to get the required multiplicity. Okay, so and whenever you see any centered lattices, just A, F, C, I, you will find these things on top, to which you will have to add each of these components, and after adding, make sure that they are not greater than 1 or less than 0, so that you can bring them back into the unit cell. Is that clear? Are there any questions you have at this point? Yes?
Could you once again show how you applied that transformation in crystallographic data?
Sure, I will do that. So the question is how to apply this transformation so as to get your basis calculated in some non-standard setting. So let us go back. So we click FD3 bar M, okay, and then when you click standard default setting, you will get what I got previously, where this is what you would get, and you would find the atom at 1 by 8, 1 by 8, 1 by 8, 7 by 8, 3 by 8, 3 by 8. Now I want to shift, I want to make this 0, 0, 0. I want the origin to be located right on top of the atom. So what I do here is, I go back and click non-conventional setting, and it tells me what sort of transformation I want to apply. So this is basically a linear transformation. You can rotate it, you can rotate the origin and all that, you can rotate the coordinate system and all that. We don't need that, we just need a origin shift. So I am going to shift it by 1 by 8, 1 over 8, 1 over 8, and then click change the basis, and then it gives me on the left hand column the standard default setting, and on the right hand column it gives me the transformed thing, where 1 by 8, 1 by 8, 1 by 8 becomes 0, 0, 0, and basically 1 by 8, 1 by 8, 1 by 8 has been subtracted from all the various bases. Three by 4, okay. Diamond cubic is 1 by 4, 1 by 4, 1 by 4. There is an atom at 1 by 4, 1 by 4, 1 by 4, and you are telling me that here it is 3 by 4, 1 by 4, 1 by 4. You put 1 by 4, 1 by 4, 1 by 4 or 3 by, because when you add this half here, all these things will automatically generate that 1 by 4, 1 by 4, 1 by 4 that you are talking about. So it doesn't matter. So I go here, I go to my get basis command, instead of 0, 0, 0, 1, okay, 0, 0, 0, 1, quarter, quarter, quarter 2, and if I click run, it generates a structure. You look at how the atoms are oriented. It is oriented with 2 atoms this way, 2 atoms that way, and then the corresponding face centered atoms here. Right? These are all the face centerings. Is that right? Now if I just change it, it is just the only thing that has happened, it has been rotated this way. There is no other difference from crystallographically, there is no other difference. Is that right? Are you able to see that? Yes or no? This one?
And then we see that the next layer, the blue atom which will be near to it, left back. But in the other case, it's on the right.
So will there be, but there will be an atom here, no? Which will now, which it's down. So
The other one is up.
it's up. It's up, yes.
No, it won't be the same. The other alternating voids
The other alternating voids
are
will start coming in. So this is actually the diamond structure. If you put 3 by 4, 3 by 4, 3 by 4 is what you get the actual diamond structure. They look the same, but I think the directions are a little bit different. So in one you would have an atom at quarter, 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 but when you repeat it, see, for example, that this one is at quarter, quarter, quarter with respect to this this corner atom, right? If I put a red atom right here, which is going to exist, then this one would be at the quarter. It will be down. Now, this direction and this direction, are they going to be the same for diamond cubic structures? The 1 1 1 and 1 bar 1 1. You'll have to think about it, right? They both may not necessarily be equivalent. Is that answer your question? They're not giving, they give the same symmetry, yes, because you have generated from the same symmetry system only. We'll have to work it out completely to actually take a look. So we'll see that later. What is that? Energy. But in this there is no real 4-1 or 4-4 to actually have an enantiomorphous pair. It's not the enantiomorphous, it just depends on how it is being transformed and rotated. I think I believe you can transform and rotate either one to make them coincide. That's what I think. You have to give it a shot. Okay. How did I restrict to one unit cell? So there are commands that are present in the main MATLAB program. That's between line numbers 61 through 678, which will essentially take care of that. Okay, that's based on some analytical geometry, which I presume you will find out how it works. Okay, but if you do this, it will work. Anything else? Nothing else. Okay, good. So let us go to the next structure that we want to create. So I want to create PDS, Palladius sulfide as we call it. Okay, and it has the space group 4,2 over M. Okay, this is the space group for Palladius sulfide, and like what we discussed yesterday, so P42 means it's basically a tetragonal unit cell, and like what we discussed yesterday, there are sulfur atoms which occupy 8k positions with XS 0.19 and YS 0.32 and ZS 0.23, and there are 3 crystallographically different palladium atoms at 2E, 2C and 4J positions. Once you specify 4J, you also have to give the corresponding fractional X and the fractional Y coordinate. So we go to our crystallographic web page, P42 over M, 84, right? Standard or default setting. In standard or default setting, whenever you talk about orthorhombic space groups, the B axis is going to be horizontal, the A axis will be vertically pointing downwards, and you will be looking at it from the C axis. So which is essentially saying that A axis is horizontal, B axis vertically pointing up, and C axis is pointing outside the plane of the paper. The simple, not confusing at all system that is being used for this structure. So there is a point called 8k, and these are the various points that you will have to generate: x, y, z, minus x, minus y, z, and so on. So 1, 2, 3, 4, 5, 6, 7, 8 points. So let us see how those 8 points are being generated.
What you just told now, this is horizontal, this is vertical. How does that matter?
Well, if you in the international tables of crystallography, if you take a look at, okay, how does this vertical or horizontal way of organizing your ABC vectors matter? So in the international tables of crystallography, which we don't discuss here in detail, you don't have 3-dimensional diagrams, you have 2-dimensional diagrams, and you can actually specify x, y, z with respect to the x. Normally whenever we talk about the fractional x coordinate, we are always associating it with A, and normal y coordinate we are associating it with B, and C with the z coordinate. But I could very well choose a system which is not that way. I could draw this as C, this as A, and this as B, right? And you have to be careful to choose your x, y, and z fractional coordinate accordingly. So whenever when you see in the international tables of crystallography, you would see a B vector pointing out to the right, A vector pointing to the bottom, and automatically it would mean that the C vector is pointing outside. Okay, and which is the same as A horizontal, B vertical, and C vector pointing to the outside. It is also possible to have a coordinate system where you look at it from the B axis. For example, in the monoclinic lattice, whenever we are talking about the monoclinic lattice, they would say that the B axis is unique. What that means is, this is A, this is C, and this would be B, or the B would be the axis which has the twofold coordination number. In that case, you would have to associate the Y with this B and not with this C. Okay, it will make a difference in the final structure that you generate. I think I have an example showing that. We will see when it comes. Okay.
So you said like the outward pointing vector is the highest, has the highest.
Usually the outward pointing vector will have the highest symmetry, or will be called as the unique axis. The B axis is the unique axis in the monoclinic structure. They will tell you unique B axis, right? I think I have a example there. We will see that. It's not PDS though. PDS is quite straightforward. So in PDS we have one 8K position. So let us open that. PDS. I did not give this to you, so you don't have it with you. So I just want you to follow right here. So in PDS, the sulfur is present at 8K position, and these are the three values. So I have named the sulfur atom with atom type 2. The x fractional coordinate, y fractional coordinate, and the z fractional coordinate are given right here. And for 8K, there are 1, 2, 3, 4, 5, 6, 7, 8. 8 additional points that I need to generate. Therefore, I have basis underscore sim s subfunction right here, okay, where I will generate all of them, and I will also make sure that the fourth column is the same as x4, which is the same type, and I will go over all these atom x, y, z fractional coordinates and pull them all inside the unit cell by either subtracting them from 1 or adding -1 to these particular coordinates to actually pull them back into the unit cell. Okay. Now I have to do this for the other atoms as well. So the other PD1, the palladium first atom, is actually present at 0, 0, quarter 1, 0, 0, 3 by 4, 1. So I can either give them like this or in the form of two separate rows like we had in the diamond structure, and I go over all these atoms. So PD1 just has 2 points, right? That's this, right? 2B, is that right? Is it 2B? It's 2B. So half of 0, half of half. 2E was 0, 0, quarter, 0, 0, 3 by 4. So 0, 0, quarter, 0, 0, 3 by 4 are just given directly. Okay. PD2 has is a position 2C, 0.50 and half, 0, half, which can also be seen here in position 2C, right? These two. Then I have PD3, which is present at a position 4J, for which the x coordinate is 0.48 and the y coordinate is 0.25 and the z coordinate is 0. Okay. However, position 4J requires some additional points to be generated because of the symmetry. So 4J right here. So it's xy0 minus x minus y0 minus y x half, y minus x half. Okay. There are negative things coming in, so I'll have to make sure that I am pulling them all back inside the unit cell. So I write another small function basis sim PD and give this PD3 alone to it, which will basically generate all the necessary points for that particular PD. So now if you see, the total number of atoms inside the unit cell is going to be 2 plus 2 plus this is 4, 2 plus 2, 4, 4 plus 4, 8, 8 plus 8, 16. There are 16 atoms that is present inside one unit cell of PDS. Okay. So we go back here to the main program. We don't have to change much here. We just have to choose the appropriate lattice constants. and choose the appropriate lattice vector. That's yeah, this one right here. Oh, sorry, yeah, you remind me. So I need to change the get basis command to be that of PDS. And that is the crystal structure for PDS. So these are the, I think, the palladium atoms, and the other ones are probably the sulfur atoms. So this is how you generate the structure. Of course, it is important for us to know whether we generated it correctly. So it's a good idea to actually go to our materials project website, choose PDS, search. Okay, so PDS 442 over M is what we generated. So we click on that, just take some time. So in this manner, you can actually generate almost all the structures that you need. It's very simple. Okay. Now this looks very complicated here. So I just remove the bonds. I remove the polyhedra. So you see all these things, all these atoms. So this is the palladium atom. This is it looking like the way we generated? Can we convince ourselves that we have generated it correctly? Yes. So this one is right here, this one is right here, this one is right here, and then you have these four atoms appearing here, and then the sulfur atoms right here. It looks a little bit skewed because MATLAB is not plotting it correctly. Okay, otherwise it should look squarish. You are looking it from the C axis. And again, if you want to yeah, so that's PDS. So the PDS is pretty simple. It's not very complicated, but you can see how this structure can get pretty complicated if you have a larger number of atoms per unit cell. You should know how to check it through this website.
So the translation of the atoms are
What did you say? Translation of the
translation of symmetry is
conserved
translation of symmetry is here.
here in this website thing. They have also plotted those atoms. So if you did not want to take a look at it, you just need to click edit crystal and then uncheck repeat atoms in the periodic boundary conditions, and you would see exactly only those atoms contained within the unit cell, which we can see if it opens up. The problem with this website is that it's just taking a little bit longer. So that is PDS for you. Now we can of course extend this a little bit. Like I showed you, you can actually print all the atoms that's a little bit more than one unit cell, maybe by saying 1.2. Now it's a little bit more than one unit cell is being printed. Okay, you can put 1.1 and you can make sure that these two atoms are actually not going to get printed. Okay. Right there. Are there any questions with this aspect? I know you may not have enough time to actually code it right now and see. You can do it later on in your at home. But this is just a demonstration for the space group P42 over M. A question? Yeah. For the generic site means you mean this one? This one? This one? Why does it have 8 sides? Because see, P42 over M, what does it mean? It means that so this is a tetragonal space group, but it is, first of all, P4 itself will generate 4. But now what you are doing is you have 4-fold rotation and you have a mirror perpendicular to it, right? So there is a fourfold rotation. It's not just a fourfold rotation, it's screw axis, right? You are performing a fourfold rotation and moving it half the unit cell. And there is a mirror that's perpendicular to it. So the set of all these operations that will be generated, that will be applied on one generic point xyz will generate these additional points. This is exactly what we did for P4, the simple case. Site symmetry is 1. So the question is, what is the site symmetry? Site symmetry means it's a general point. The particular point is not lying over any symmetry element. That's what it means. If it starts to lie over a symmetry element, the multiplicity reduces. For example, the point 4j, the multiplicity is m. That means that point lies on the mirror, right? It lies on x, y is 0 or z is equal to half. It lies on a mirror. Once the point starts lying on a symmetry element, the number of additional points that get generated by applying all symmetry elements that is appropriate for the space group P42 over M will be lower than what you get for a point that is not lying on a symmetry element, like a general position. Again, the generation of this will involve these matrices, right? We talked about for P4, remember we used a simple matrix and I showed you how these points were generated. For this space group also, there are a couple of different matrices that you can generate and study and apply it to a general XYZ point and generate all these additional points. It's just possible, but we are just not doing it in this course. Okay, that is not our goal, because people have done that and given these tables to us. We want to know how to use them, how to use them to generate our structures. Is that okay? Okay. So first you tell me what is, okay, what is meant by P42 over M. So first question is, what is that? P42 over M is a space group, right? It's one of the space groups. Of the 230 space groups, is one of the space groups. P42 over M is basically the Hermann-Morgen symbol for a space group, and in this particular space group, the symmetry elements that have been applied is a fourfold rotation, but not just a mere fourfold rotation, but after applying the fourfold rotation, I have to move it up along the c-axis by half the unit cell. Not only that, I also should make sure that there is a mirror that's perpendicular to it. All these symmetry elements are there in that space group. By means there is a mirror that is perpendicular to the axis that contains the fourfold rotation. P2 over M means there is a mirror that's perpendicular to the axis that contains a twofold rotation. That's what it means. Yes, exactly. 4 suffix 2 over M is present in one slot. It refers to just the c-axis. That's it. Or in other words, if you want to be precise, it is P1 4 suffix 2 over M. But these 1 don't mean anything. So we just write it as P4 suffix 2 over M. Is that okay?
Sir, we read about compound symmetry operations in the past, and there was a operation rotoreflection.
Yeah.
In which we came across the symbol S2, S4 means rotation followed by a mirror.
Yes.
So is S2 the same as 2 by M?
Is S2, we studied another set of symbols called as rotoreflection, and is S2 the same as 2 over M? I will show you that slide. S2 is twofold rotation followed by a mirror, right? So it means an inversion. It means an inversion, not a mirror. It's not twofold rotation. Perpendicular to it, there is a mirror. It's just twofold rotation, right?
But is the mirror perpendicular to that twofold rotation axis?
Yes, always. If I write 2 over M, it means that the symmetry elements that are present are a twofold rotation and a mirror that is perpendicular to it.
In S2 also that is
No. S2 means a twofold rotation and a mirror. not and a mirror, sorry, two-fold rotation, and then you apply a mirror operation to it. So this atom is not there. S2 means I have applied a two-fold rotation and then I applied a mirror. So this intermediate point is not generated. 2 over m means the two-fold rotation is also present and the mirror is also present. Yes. Yes. If I say 4 suffix 2 over m, it means there is a four-fold rotation and screw and the translation by about half the unit cell, and there is also a mirror perpendicular to it. So it's not.
So in 2 by m, both 2 and m are independently existing.
Yes, they will exist. Yes.
But in S2, they are not independently existing.
Correct.
They are only present as a combination.
Correct. That's what happens in that's what happens even in say 4 bar. Say for example 4 bar, four-fold rotation and an inversion. Individually 4 and 1 bar is not existing. Right? They are not. For example, if you look at the screen, individually 4 and 1 bar is not existing. 4 bar together both have to be applied consecutively to generate that operation.
But even in case of S2, when we apply the two-fold rotation, we must be applying it about an axis. So the mirror, is it perpendicular to that axis? The mirror plane?
Yes,
It is.
it is perpendicular to that axis. So in S2, it is two-fold rotation, mirror. This intermediate point is not generated. In fact, S2 is therefore just 1 bar. Okay. But if I say 2 over m, it means there is a two-fold rotation and there is a mirror perpendicular to it. So consequently, in 2 over m, you will have this. Right? There is a two-fold rotation and a mirror that is perpendicular to it. Are there any other questions here? Is okay? So we have a couple of more examples. In particular, I think I wanted to talk about this one, which is CAMG SI206, which is where a little bit of confusion comes with regards to how you choose your A axis, B axis and C axis. Okay, we will do that in the next class.